Ouais.
Comme ça, on y explique la
Martien.
Ouais, mais
Nicole, ils entendent bien.
Yeah, but I don't know if Carlo
le son, là, je sais pas si vous entendez la réponse.
it seems that we have our microphone on.
Carlo, do you hear us? Can you hack or something? Oui, j'ai vu, mais on
Ouais, c'est surtout la question, si on les entend ou pas.
Can you speak so that to see if we can hear you?
C'est un.
I believe you need to enable me.
Moi j'ai assisté la barre alors.
Now I can unmute myself.
Perfect. Perfect, Carlos.
Hello, good afternoon.
Good afternoon. Hello. Welcome. Patrick, bonjour.
Bonjour, bonjour à tous.
Impeccable.
Je
Bienvenue.
vous entends bien et je vous les dimanche. Je suis désolé de ne pas être présent avec vous, mais un minimum, je vois et j'entends correctement.
Impeccable.
Merci.
Merci.
Les jetons dessus.
Hello, Michael. Do you hear us?
Yes, I can hear you loud and clear.
Lovely.
Merci.
Very nice to have you here.
Yeah, thank you very much.
Cheers.
Looking forward.
Cheers.
Non.
Est-ce qu'il faut qu'il fait quelque chose?
Non, tu vois, ça marche. Ouais, ça marche. Je l'enlève. Ah, ça marche. Ouais, c'est ce que j'avais bien fait. Bah attends, je vais me connecter sur le lien que t'as envoyé sur un SD.
Ah oui. Ah oui, j'ai reçu un email. Je pense que tu vas aller.
Ah, ok. Après, ici.
Sí, sí, somos.
Sí, ça marche.
Sí, claro.
Hola, ¿me escuchan?
Oui, t'as un délai, c'est normal. T'as un délai de quelques heures.
Voilà. There's a delay 15 seconds.
Okay.
10-15 seconds.
Okay.
Oh,
It's weird because
Did you succeed in the
yeah, with the sound of everyone.
unmute works?
Yeah.
Ouais, c'est bon. Mais en fait, il y a je pense, les fils de la télécommande.
Ah ouais? Mais c'était avec le 6 là?
Ouais, en fait, c'était étoile 6.
Étoile 6.
Étoile 6.
Je vais dire à
Alexis.
Alexis que c'est bon, il a réussi, c'était étoile 6, on peut le faire.
Oui, on le connaît sur Chicken.
C'était 6. Oui, parce qu'il faut que tu sentes.
C'est bizarre parce qu'ils n'arrivent pas. C'est comme si là, c'est une.
Maintenant, le lien que j'ai mis.
C'est pas le même lien que c'est le lien sur les.
C'est le lien envoyé sur un.
Je ne veux pas les volumes.
Il
faut utiliser les choses.
C'est pour ça, moi je suis là.
C'est comme ça. C'est au temps d'abonner. Ça compte en visualisation.
Ouais, je me suis.
C'est comme ça, moi je trouvais que le visualisation
Ouais, je vois.
Vous pouvez m'envoyer les liens sur son.
On demande quoi de lui faire, jamais.
Ah oui. Ah oui. Un point du milieu.
Si tu en as une ou deux, je vous laisse. Ah bah moi je suis là jusqu'à maintenant.
Ou ce sont des commentaires.
Ne pleure pas forcément. Ce serait pas bon. Non, c'est surtout bien sûr. Ça sera pas du tout. Ça a des questions sur son présent si je m'occupe. C'est ça.
Qu'est-ce que je fais? Yeah, I can see them blinking at these. It works. Breaking at the same time. Good sign. This is great. You know, I've never seen a demo in a.
No, yeah, it's great.
Very, very good.
In fact, it was really nice because I made demo paper like 2 months ago. So I have like the
setup was ready.
It was like ready. So it's perfect.
It was red?
Yeah, not great. I actually used the same thing that we use at this internship that we read.
Yeah.
More or less the same.
How did you get the charts? It's the middle ones. Is that a little red thing? Is that a little dashboard?
This one?
Yes.
Yeah. But you have to format like it's kind of weird because the documentation is not like very good. But you have to format the JSON.
But it's still a dashboard. There's nothing.
Yeah, it's nothing. Also, no great dashboard.
Very good. Very good.
All the nodes in the network. It's nicer because we have all the information.
It's nearly industrial design.
Then you have a CAN to USB like adapter.
Yeah, it's a CAN transceiver, and I have in the background I have a Python interface which receives the data and I can use it. Yeah, I will explain all the.
Oh yeah, I'm getting it.
And yeah.
Non, mais c'est juste.
C'est pas un service à faire.
Xavier.
Ordinairement,
c'est la même. Même.
oui, je quand même
Ouais, et en fait, finalement, ouais. Et ça, c'était ça. Mais j'ai trouvé parce que je suis allée dans une bibliothèque, je donnais mon nom, c'était je donnais mon nom, généralement associé avec un fichier. Je mets ça avec un fichier, je sais pas. Puis après, un jour, je me suis rendu compte, en redonnant ma carte idéale, dans le nom, on me donnait quand même. Non, en fait, j'avais mis ça. Et ça m'a Okay. So, welcome everyone. We are pleased to be together to hear the defense of Fabian Rincon Vija. He's going to give the results of his research on enabling robust wireless communication for battery management system in electrical vehicles. So today the jury is composed of several researchers. So we have Thomas Vatain, who is the research director at INRIA. He was one of the reviewers. The other reviewers is online, I guess. It's Carlos Alvera Boano, who's professor at Graz University of Technology. Can you hear me well and the distance? Okay, thanks. Then we have as well Michael Gidlund, who's professor at Mid-Sweden University. And we have the thesis advisors, which are present, Nicolas Montavon, professor at IMT Atlantic, and Yorgos Papadopoulos, who's professor at IMT Atlantic as well, and Samuel Crégu, who's an expert in BMS group, Renault Group. And myself, I'm Katia Jaffras-Munzer, I'm professor at Toulouse INP. So you have 45 minutes to present your research work, and then we'll engage into a question and answer session.
Okay. So hello everyone, thank you all for being here. For me, it's such an honor to have you here in my PhD thesis defense, which is called Enabling Robust Wireless Communication for Battery Management System in Electric Vehicles. During this presentation, I will start with the context and motivation around the wireless BMS. Then I will present the state of the art on wireless network from which we get the inspiration to implement our proposal. Then in section 3, I will start with my contributions, where I will start explaining how we enable robust wireless communication for critical applications and how we use this proposal to implement the Renault Zoe wireless BMS. Then in section 4 will be the time to talk about the wireless BMS state mode and how we can enable the autonomous balancing with the introduction of this wireless interface. Chapter 5 is called Beyond Wireless BMS, because here we will have a discussion around the new opportunities in the BMS software architecture that the introduction of this wireless interface brings to the system. Then, at the end, I will present my conclusions and the results of the vehicle test that we managed to execute. Let's start with the context and motivation around the wireless BMS. Electric vehicles are considered as the present and future of transportation. The European Union wants to reach the net zero of greenhouse emissions by 2050. And for this reason, they have voted to ban the sale of internal combustion vehicles from 2035. Even if the electric vehicle is not the miracle solution for our environmental issues, its carbon footprint is 2 to 4 times lower than an internal combustion engine vehicle. So in this context, the research and development around the electric vehicle has been multiplied in the recent years. In an electric vehicle, the battery is the most important element because without any doubts, the development of the lithium-based cells has allowed us to put these electric vehicles in the center of the future transportation. As the lithium cells has high energy density, low cell discharge rate, and negligible memory effect. Typically, in a battery pack, we put a lot of multiple battery cells connected in series and grouped into modules. As an example, in the Renault Zoe, we have 96 cells which are grouped into 12 modules that can reach up to 400 volts. However, despite the big advantages of these lithium cells, abnormal conditions may produce failure, fire, or even explosion. So it is very important to ensure the recommended voltage and temperature conditions which is often called the safety window. For this reason, every vehicle in the road has a battery management system, BMS, which is a set of sensors which measure the cell voltages, the module temperature, and the battery pack current in order to execute some calculations like the state of charge of the cells, the state of health of the battery, and to ensure that all the cells have the same level of charge. With this data, the BMS will allow or disallow the charge and discharge of the vehicle. It will set the maximum input or output power from the battery. And again, all of this to keep the battery pack inside this safety window in order to avoid catastrophic consequences. The BMS typically use a master-slave architecture, where the master is the central unit which has the computing unit, which executes all the calculations, and the peripherals has the voltage and temperature sensors together with the cell balancing actuators. Typically, the master and the slaves communicate through a wired interface, as you can observe in the diagram. The BMS has two modes of operation, active and sleep mode. The active mode is used when the vehicle is in charging and driving state. In this mode, the central device has to watch continuously the status of the battery, and to do this, it has to receive periodically a new measure from all of the sensors. In the case for the Renault Zoe, this period is 100 milliseconds. In the sleep mode, we use this mode when the vehicle is in parking state, where the BMS must go to an ultra-low power mode operation, and the only mission is to guarantee the battery pack balance during this mode. Lately, the industry has seen a big interest on removing this wired interface between the master and the slave and replacing it with a wireless link, as you can observe in the picture. The main reason is that this copper wiring harness is heavy and occupies space inside the battery pack, which would be better to fill with additional cells. In addition, this copper wiring harness reduces the flexibility of the battery pack and increases its complexity, which means more time and money is spent in the development and assembly phase of the battery pack. In addition, if we remove this physical interface, we will also remove the failure risk in the communications associated with the degradation of the physical connectors of the wired bus. But because the BMS is a critical system, a wireless network inside this system should guarantee high reliability, bounded latency, and low energy consumption, which means that the central device must be able to receive all of the messages from the sensors within a specific time interval, which is 100 milliseconds for our Renault Zoe case, and all of this without having a negative impact in the autonomy of the electric vehicle. So in this context, the Renault Group has joined forces with the EMT Atlantic in order to start this PhD project around this wireless BMS system. From this project, we can summarize the main contributions in these main four items. The first one is that we propose a robust framework to enable robust wireless communication for critical applications, and then we use this framework to implement the active mode of the wireless BMS. We also propose a low power mode for TSCH networks with the star topology, where we are able to turn off completely the central device of the network, and while keeping the network synchronized, and then we have used this proposal to implement the sleep mode of the wireless BMS. Then we also open the discussion around the BMS software architecture revolution that the introduction of this wireless interface brings to the system. Finally, all of our proposals has been implemented and tested in a real-world scenario, which is an electric vehicle, in our case, the Renault Zoe. So with this context in mind, let's talk about the state of the art around wireless networks. But because of the tight requirements of our critical application, we decided to center our review in these three well-known protocols. The 802.15.4 IEEE standard, which is the reference document for low-rate wireless personal area network, in particular the LLDN and the TSCH MAC protocols that were introduced in the 2012 amendment and from which only TSCH was kept in the last update of the standard. We also have the Bluetooth Low Energy, which offers short-range wireless communication and that has been applied to multiple applications. And finally, we have wireless IO-Link, which offers reliable, real-time deterministic wireless network for factory automation. After having reviewed all of these options, we have managed to identify 5 key elements and mechanisms that will enable a wireless network to meet all the requirements of a critical application. The first one is the time division, which has been adopted by all of our reference documents, and where the idea is to take the time, divide it into small intervals, which are called time slots, and then take a bunch of these time slots and put them in a bigger structure called a slot frame, and then repeat the slot frame over time. The idea is that at each time slot, the nodes are able to execute a different action, like sending a message, receiving a message, or just waiting until the next active time slot. With this, the network will be able to avoid message collisions within the nodes, within the network, and also it will enable low power operation because the nodes will be required to use their radio only when it is absolutely necessary. The second mechanism is the frequency diversity, which has been adopted by almost all of our reference networks, except from LLDN, for which the standard defines to use the same radio channel for all the data exchanges. The idea here is to use multiple radio channels in order to gain robustness against external interference and to avoid multipath fading problems. There are multiple ways to use this frequency diversity mechanism. For example, the time slot channel hopping TSCH MAC protocol proposed to use a different radio channel for each time slot, as you can observe in the diagram. But for example, Bluetooth Low Energy proposed to use the same radio channel for all the time slot in the same slot frame, which in this technology is called events. But then for 2 different events, we will use different radio channels, as you can see again in the diagram. Next, we have identified the centralized scheduling mechanism, where the idea is to predefine with a central unit how we are going to manage the data exchange within the network, and this scheduling function would be defined with different objectives in mind. In particular, in our reference document networks, we have found 2 very good options to enable high reliability and bounded latency. The first one is the scheduling function proposed by LLDN, where we have a super frame that can be adapted to multiple sizes of networks, where we have different kind of time slots with special functions. We have time slot for synchronization, network management, dedicated uplink transmission, and retransmissions. It is worth to mention here that for TSCH, the standard does not propose any kind of scheduling function, as they prefer to leave this task to the upper layers. For our next example, which is wireless IO-Link, we have a predefined scheduling function that allows a network with 1 central device and maximum 8 nodes to update one message of maximum 12 bytes from each node every 5 milliseconds. What we have found very interesting in these 2 examples is that the key to achieve a high reliability and bounded latency is to well manage the retransmissions. In LLDN, they propose to use the group acknowledge mechanism, where the idea is that at each superframe, the central device will inform the network which messages were lost, and based on this information, the network will distribute the retransmission time slot. However, the standard limits to maximum 1 retransmission per node at each slot frame, and they also limit the number of retransmission time slots to maximum half the number of nodes in the network. For wireless IO-Link, we have a predefined superframe structure, which is called W cycle in this technology, which is divided into three subcycles. The idea is that at each subcycle, the node have an opportunity to send its message to the central device. So in a superframe, each node has a transmission opportunity and 2 guaranteed retransmission opportunity, which would help to increase the reliability and the bounded latency requirement. Finally, we have the channel deny list mechanism, where the idea is that the network is able to identify which channels has a bad performance and set them to avoid these channels. Because even if our network uses a different radio channel at each time slot, the most appropriate centralized scheduling function with the best retransmission policy possible, if the network uses channels with bad performance, the system is not going to work. In our reference document, we have the Bluetooth Low Energy says that it will be okay to use a channel denial list mechanism, but they do not specify how the network should identify these bad channels or when they have to execute this channel denial list update. For TSCH, the standard does not specify neither a channel denial list mechanism, but in the literature it is easy to find multiple proposals to enable a channel denial list mechanism in TSCH networks. So as you have observed, none of our previous reference document networks will meet by themselves with all of our predefined mechanisms in order to achieve a robust wireless communication. So in this context, we have decided to propose a framework to enable robust wireless communication for critical applications and then use this framework to implement the Renault-Zoe wireless BMS. The outcome of this chapter 3 has been submitted to 2 international conferences during my PhD project. So, based on the state of the art, we have decided to use a network with a star topology, as our network will have always the same number of nodes, and it is very important for us to have the same energy consumption between all of the nodes. With this topology in mind, we have decided to go with the Bluetooth Low Energy physical layer that allow us to have up to 2 megabits per second of data rate and 37 radio channels. On top of this, we decided to use the time slot channel hopping MAC protocol in order to take advantage of the time division and the frequency diversity mechanism. And because with this MAC protocol, it is possible to design a special scheduling function with an appropriate channel denial list mechanism in order to meet with the requirements of our critical application. On top of this, we will have our application layer that, in our case, will be some kind of software for the wireless BMS. But now let's talk about our wireless BMS TSCH scheduling function, which is based on a modified version of the group acknowledge mechanism. To do this, we have set a slot frame with a duration equal to the target refresh time, which will change from one application to another, but in our case, it would be 100 milliseconds, for example. Then we will have a different kind of time slot with a specific function. As an example, the first time slot is a classic beacon time slot where the central device could send a synchronization message to synchronize the network, but it also to make it visible to the nodes that want to rejoin the network. Then, every node in the network will have a dedicated uplink transmission time slot where they will have the opportunity to send its message to the central device, where the central device is not required to send an individual acknowledge. Because after this static part of our slot frame, the central device will have 2 time slot opportunities to send 2 times the group acknowledge message, where it will inform to the network which messages were lost in the static part of our slot frame. Based on this data, the network will understand which is going to be the distribution of this dynamic part of the slot frame dedicated for the retransmission management. But let's see some examples in order to understand how this is going to work. Here we have the best case possible where everything is perfect and the master has received all of the messages, so it will inform this to the network and all of the nodes can go to sleep until the next slot frame. But for example, it may happen that the messages from the node 3, 5, and 8 were lost in the first part of the slot frame. So these 3 nodes, they will understand that they have to use the first 3 time slot to execute the retransmission, where the first time slot will be used by the node with the lowest ID, then the second, and then the third one. They will also understand that in the 4th time slot, they will receive another group acknowledge from the central device, informing if everything was okay or not. In the affirmative case, they all can go to sleep until the next slot frame, but it may happen that they are the messages of the node 3 and 8 that are still missing. So they will use the next 2 time slot, and they will receive another group acknowledge in the 3rd time slot. The idea is that we are able to repeat this process until the end of the slot frame or until the master has received all of the messages. With this mechanism, we are able to give multiple retransmission opportunities to the nodes according to the needs of the network at each slot frame, helping to improve the reliability of our system and to meet the golden latency requirements. For the channel denied list mechanism, we have instructed our central device to use the static part of the slot frame to identify which channels have a bad performance and create this channel denied list. Then after a while, it will share this channel denied list to the nodes, and then the network will understand that they are not able anymore to use these channels. However, after some time, the network should be able to test again these bad channels to check if they are good to use again or not. To do this, the central device will take one channel at a time, and it will inform to the network that this channel is in recovery mode. So the nodes will understand that they are able to use this channel for the first part of the slot frame, which is the static part, but not for the second one. So in this way, we can check if the channels are good to use again without compromising the performance of our network, because the group acknowledge and the retransmission time slot will always use channels with good performance. So with this framework in mind, we have decided to implement the wireless BMS active mode for the Renault Zoe battery pack, where we have one central device and 12 nodes. For the hardware, we were able to use these custom boards provided by Texas Instruments, which are ready to plug in the battery modules of the Renault Zoe. In these nodes, we have a BMS ASIC, which has all of the necessary voltage and temperature sensors for the battery cells. And we also have a radio frequency microcontroller. For the software, we were able to use a TSCH implementation provided by Texas Instruments, which was ready to work in this microcontroller. So we took our framework and we designed our scheduling function for the wireless BMS, where we have a load frame duration of 100 milliseconds with a time slot length of 3.3 milliseconds, which gives us 30 time slots in a single slot frame. And then we took this scheduling function and we adapted the TSCH implementation that Texas Instruments provided to us. And after several months of hard work, we managed to deploy this network in this Renault Zoe battery pack that we will have in our laboratory. With this battery pack, we were able to execute several tests, but in particular, we executed 2 tests during 1 week each. The first one without the metallic battery pack cover, as you can see in the picture, and the second one with the metallic battery pack cover in place. After these experiments, for each experiment, the master was supposed to receive around 60 million of messages from the node, and the results showed that the network with our dynamic retransmission system managed to deliver all of the messages within 100 milliseconds, which is a major achievement, as it demonstrates that our proposal in this TSCH network over the Bluetooth low energy physical layer managed to provide high reliability and bounded latency. But then we decided to test our system in an environment with high external interference. So to do this, we set up 2 Wi-Fi networks in the channel 6 and 11, and then we use for laptops to create constant traffic using the SCP protocol. And with this setup, we execute 2 tests. The first test was without the channel denied list mechanism enabled, and the second test with the channel denied list enabled. So in the first test, even with our dynamic retransmission mechanism and with our super robust system, the performance of the network was not the best one, because our reliability only reached 92%. In fact, in this diagram, the light blue area represents the channel stability of the BLE channels during this test, where, as you can observe, it is very easy to identify the impact of our 2 Wi-Fi networks, where we have some BLE channels with a stability lower than 30%, which is really bad. But then we executed again the same test, but with the channel denied list mechanism enabled, And here the network managed to lose only 13 messages out of more than 200,000 messages, which is very good. But the best part of this experiment, of these results, is that these 13 messages were lost only at the beginning of the experiment, while the master was learning which channels has a bad performance and put them in this denial list that was shared with the nodes. In the diagram, the dark blue bars represent how many messages were sent per channel during this experiment. And as you can observe, the channels with high interference in the previous test were barely used in this one, as our algorithm has detected them and have blocked them for the network. Finally, for the energy consumption, we managed to measure it using the energy trace tool of the Texas instrument, from which we were able to obtain this current consumption profile over the time for the node 4 of the network and for the central device, where, as you can observe, it is actually possible to identify the operation of our scheduling function, where we have the common synchronization time slot at the beginning, then the node 4 uses the 5th time slot to send its message to the central device, and then after a while we have the 2 time slot for the group acknowledge. So with this tool, we obtain an average current consumption for the radio frequency microcontroller of 0.42 milliamps, which is very good as it meets with the requirement that we have set for the project at the beginning, but also because compared to the average current consumption of the BMS ASIC, which is around 15 milliamps, it's very small, which is a very great news, as it demonstrates that the inclusion of this wireless interface does not affect the energy consumption of the overall system. And with this, we have managed to design a complete active mode for the wireless BMS system. And with this in mind, it is time now to talk about the sleep mode of the wireless BMS and how we can enable the autonomous balancing with the introduction of this wireless link. The outcome of this work has been also submitted to an international conference during my PhD project. So when we talk about the sleep mode, we have 3 main conditions. The first one is ultra-low energy consumption, where the system must be able to turn off the BMS ASICs, and we have set a maximum energy consumption of 70 microamps per slave. The second condition is that the system must guarantee a fast wake-up process, where once the system has received this wake-up interruption from the central device, from the EV central computer, the BMS must guarantee a new measure from all of the sensors within 1 second. And the last condition is the same that we discussed in the first part of my presentation, which is to ensure the battery pack balance. So in a wired BMS, it is very easy to implement this sleep mode because we actually have a physical interface to wake up all of the system almost instantly. But for the wireless BMS, it is impossible to completely turn off the slaves because we don't have this physical interface. It is possible to turn off the BMS ASIC, but the radio frequency microcontroller must remain active. And it should remain active but synchronized, because if they lose the synchronization, they will be required to keep its radio on in receive mode continuously, which will consume a lot of energy, and which is the opposite of our main objective in the wireless BMS sleep mode. So a typical approach would be to keep our network topology and just modify the scheduling function, where the master would be required to send a synchronization message periodically, every T-sync. This T-sync value is a trade-off between the wake-up time and the energy consumption. If we set up the T-sync very short, like 50 milliseconds, the wake-up time would be also very fast. We would say 100 milliseconds, but at the same time, the energy consumption would be high. So in a system like this one, where we have a requirement of a wake-up time maximum of 1 second, a T-sync value for 400 milliseconds would be an adequate value. The inconvenience of this typical approach is that this will require to keep the wireless BMS master active, which is not the preferred option for the car manufacturers, because this wireless BMS master is powered by the small 12-volt battery of the vehicle, which does not have a big capacity and which is not very easy sometimes to recharge. So the main objective for the car manufacturers is to keep as low as possible the energy consumption from this battery pack, from this small battery during the sleep mode. For this reason, we have decided to propose a wireless BMS sleep mode where it is actually possible to completely turn off the wireless BMS master while we keep the network synchronized. To do this, as you can imagine, we have to modify the topology of our network. And then we will use a new scheduling function where the principle is still the same. We have to send a synchronization message periodically every T-sync. But in this case, it's going to be at each time a different node, the entity who will send this synchronization message. And then the network will be able to keep its synchronization. Which is very interesting of this, with this split mode is that if the nodes include the battery cell voltage measure in each synchronization message, after a while, every node in the network will have a complete picture of the balance status of the battery pack, and they will be able to execute the necessary tasks to ensure the battery pack balance, and all of this without any intervention of the BMS central device. For the wake-up procedure, once the central device has received the wake-up interruption from the EV central computer, it will just turn on its radio in receive mode, and it will wait for a synchronization message. Once it has received the synchronization message, it will get the timing of the network, and it will be able to send a wake-up command in the next time slot. Then the network will switch to active mode, as you can observe in the diagram. So at the end of the day, with our wireless BMS sleep mode, the nodes are required to wake up during 2 time slots every T-sync in order to keep the synchronization with the network and to check if the central device has a wake-up command to send. For the wake-up time, it is still a consequence of the T-sync value and the moment between 2 synchronization messages where the BMS central device has received the wake-up interruption. In this case, we have the worst case, because the central device has received its wake-up interruption just after the node 3 has sent its beacon. So we will have to wait all this T-sync period until receiving the next synchronization message. On the other hand, we will have the best case when, in this case, the wake-up time will be very short as the wake-up interruption has arrived just before the node 4 has sent its synchronization message. So we have took this whole idea and we have implemented it again with a lot of work and months of implementation. We have put it in our wireless BMS prototype for the Renault Zoe with a T-sync of 400 milliseconds. With this, we managed to execute several tests. In particular, we instruct, this one where we instruct the network to execute 100 wake-up procedures and to wait during a random sleep interval between these wake-up procedures. Then, for each case, we measure the wake-up time and we put the results in this graphic, where, as you can observe, we obtain like a bunch of different wake-up time values, but all of them below the 400 milliseconds limit that is primarily set by the T-sync value, which is very good as we meet with the requirements set by our wireless BMS application. For the energy consumption, we executed the measure in the same way as in the previous case for the active mode with the energy trace tool, and we obtained an average current consumption of 60 microamps per slave during the sleep mode, which is very good as it meets our requirements, but it is also negligible compared to the module capacity of the electric vehicle. So at this point, we already have a complete wireless BMS solution designed, implemented, and tested, which meets with all of the requirements set by our application. But the inclusion of a radio frequency microcontroller in fact opens the door to a new chapter in the BMS software architecture, as it is an opportunity to improve some characteristics and even reduce cost. To this point, our microcontroller oversees the TSCH network operation, which is the main reason why we include it in the notes. It also manages the UART interface with the BMS ASIC, and in our system, it retrieves a new measure every 100 milliseconds. Finally, it also executes some kind of voltage and temperature processing because the values returned by the BMS ASIC are not the clear values like in the good units that our central device requires. So this microcontroller executes some kind of very simple mathematical operations to retrieve the good units. But then, with my advisors, we decided to include some other functionalities to our wireless BMS network system. And to illustrate this, I present here the scheduling function for the Renozoe wireless BMS for the central device and for the first 3 nodes of our network, where you can identify the network operation with the dedicated time slot and the group acknowledged time slot, this scheduling function allows us to send 1 message every 100 milliseconds. But our nodes, they are actually capable to compute or to retrieve more measurements during this time interval. So we have decided to use this synchronization nature of our TSCH network to instruct the nodes to retrieve 5 measures during this interval at the same time, and then to compute the average of these 5 measures and report this data to the BMS central device, where, as you can imagine, this simple operation actually increased the precision of the voltage measurement and, by consequence, the precision of the algorithm's estimations in the BMS. To illustrate this and to demonstrate this point, I compared both systems, where the system where we only take 1 measure every 100 milliseconds, and the system where we take the average of 5 measures every 100 milliseconds. And the results show that the variance of the measurement was reduced by 1/2 when we compute the average of 5 measures instead of only reporting 1 measure every 100 milliseconds. But then we wanted to see the capabilities of these low-power microcontrollers with more complex operations. And the first algorithm that came to our mind was the state of charge estimation. To test this one, we decided to use a very robust algorithm, which is the Kalman filtering state of charge estimation, which actually was developed by the BMS team at Renault for the Renault Zoe, and which was implemented in MATLAB Simulink. So we took this robust algorithm and we generate the code to embed it in our wireless BMS implementation. And then we noticed that each slave required around 6 milliseconds to complete a new state of charge update for the 8 cells of the module. So we decided to modify a little bit our scheduling function in order to give enough free time at the end of the slot frame to each slave. So with this, our system is now capable to update all the 96 state of charge of the cells every 100 milliseconds with a very robust Kalman filtering algorithm, which is kind of amazing. And this is the first step of the concept that we call the smart module, where we have a battery module with a computing unit, which is actually capable to completely monitor the status of the battery cells inside this module, where this unit will be capable to compute the state of charge as in our system, but also the state of health. We will be able to store in memory the lifetime conditions of the battery cells, which will be very useful for the second life applications, and even to execute some self-diagnostic mechanisms to report if everything is okay with the battery cells, or with the BMS ASIC, or even with the radio frequency microcontroller. So at this point, we have reached the final part of my PhD project, where we have decided to test all of our proposals in a real-world environment. So we took the battery pack that we have in our laboratory, we put the metallic cover, and we take it to the specialists at the Renault Development Center in Paris, where they managed to put this this battery pack in a Renault Zoe, as you can see in the picture. And then with this vehicle, we executed several tests. Actually, the same test that we have executed in the laboratory, where we have obtained a very similar performance results, which is a very good news because it means that our dynamic retransmission scheduling function in this TSCH network with the Bluetooth low energy physical layer actually delivers high reliability, bounded latency, and low energy consumption in a real environment. We also did not observe any electromagnetic interference coming from the powertrain of the vehicle or any perturbance in the other radio frequency system of the electric vehicles coming from our wireless BMS system. And we also were able to test during weeks and weeks the capability of our sleep mode to keep the synchronization of the network without intervention of the central device, which is very good. We also repeat this Wi-Fi interference experiment. So we put these routers like outside the vehicles in the road and inside the vehicle with the 4 computers. You can imagine the amount of wires everywhere. But with this, we were capable to see that even if the system is inside this metallic enclosure, which is the battery pack, and in addition, this battery pack is inside the vehicle, which can be seen as another metallic enclosure, the system is still sensitive to external interference, and a channel denialist mechanism is absolutely necessary. Another experiment that we managed to see was to check if the network was accessible from the outside of the vehicle. So to do this, we turned off the central device inside the battery pack, which was in position A in the diagram, and we took external master and we put it around the vehicle in different positions, as you can observe in the diagram. And then we measured the received signal strength from each node and check and demonstrate that we were able to communicate with the nodes that were inside the battery pack, which is some kind of good news and bad news. It is maybe good news because it opens the door to a potential opportunity for fast diagnostic of the battery pack without needing to mount it from the vehicle, which maybe one day we can have it in the after-sale life of the vehicles. But it is also some kind of bad news because it means that the system is accessible from the outside of the world, which means that we are required to implement the state-of-the-art of wireless network security, which is not like a big problem because if we take the example of the 102.15.4 standard, it already provides a specific mechanism and protocols to achieve a system with the good levels of confidentiality and integrity for the data of the network. In addition, these algorithms are based on the advanced encryption standard, which is also very good, as most of the low-power microcontrollers used in this kind of networks already have some hardware accelerators that make the encryption and decryption process very quickly. However, for the system to achieve this level of security, the transmitter and the receiver must have the same security key to execute the encryption and the decryption. And around this element, we have found the first open question around the wireless BMS, which is the wireless BMS security, and which will be the best way to share this common key between all the nodes at each network in an assembly line of battery pack. So, because maybe is it easier to, for example, pre-download this key to all the nodes in the network prior to mount them in the battery pack, but would it consume a lot of time for the operator? Or maybe it is easier to put the same key in all of the nodes and then for each battery execute some kind of public-private key mechanisms in order to reach the security level required. But which will be the performance of this mechanism where we have like a bunch of multiple networks trying to connect with the central device? The second open question that I found was around the wireless BMS safety, where the main question is which would be the best way to achieve an automotive safe level system where we are able to use the computing capacity of the slaves, but without losing the cost attractiveness of the wireless BMS. Finally, the last open question is around the battery cell second life, because I do believe that the wireless BMS introduction would make easier the transition of these battery modules from the vehicles to a second life application. But I also think that it would be easier if we are able to use battery modules from different car manufacturers without having to change the BMS hardware and only executing some kind of software update. But to this to be possible, it will be necessary to have some kind of wireless BMS standardization, which is not at all the case today. But whatever are the answer to these open questions, it is important to know that the wireless BMS is a reality. We already have in the road some vehicles with some kind of these systems, and we have demonstrated during this PhD project that it is actually possible to achieve a robust wireless system for such a critical application. Finally, here I have this last slide with the articles that we managed to publish with my advisors during this PhD project. And with this, I will finish my presentation, and I would just like to thank you all for your attention. And I'm just looking forward, and I hope that we'll have a very good discussion around my results. So thank you so much.
Thank you very much, Fabian. So now I think we will engage in this welcome discussion that you are talking about, and I will leave the floor first maybe to the furthest away reviewer of this work, which is Carlo, if he agrees with this proposition. Yes? So you can go ahead. I don't know if we can hear you.
We don't hear you, Carlo.
Maybe you have to activate the microphone in the, because you are the admin, Nicola. You have to activate the microphone for.
It's okay, Carlo.
Yeah, now I can be unmuted. Thank you very much. So yeah, first of all, you hear me well?
Yeah, perfect.
Okay, good. Yeah, so thanks for inviting me as an examiner, first of all. And Fabian, I would like to first of all congratulate with you because it was a very nice thesis and an equally nice presentation, very clearly structured and very illustrating all your work you did. So I really appreciated that. About the contributions, I think they were very timely. I think the BMS is a very nice and novel topic, and seeing it being concretely applied to the Renault Zoe and seeing it in a real world system, I think this was really a very highlight. I think that was the thesis. Now, I would like to kind of enter a nice discussion with you, and I have a list of questions, but perhaps I would like to start from the general idea from behind the networking protocol. So perhaps if you can go back to slide 15 or the very first set of slides.
Yeah.
I would like to reflect why you chose the approach you did, which is absolutely great. When you were saying that you have been considering different options, you have dismissed classical theory. Right? I would just like to have a discussion on why this was the case. So, in the end, it seems that you use a star topology, that you actually like BLE's physical layer mode, which has a very high throughput, 2 megabits per second. BLE does use TDMA, BLE does use kind of deny listing. In principle, you can also use like BLE 5.2 with these asynchronous channels to broadcast message to the peripheral nodes. So, what was one of the main reasons for you to discard it? Let's say like this.
Okay, can I answer now? Yeah.
Yes.
Okay, so I was kind of expecting this question, and I have thought at the time I thought a lot of why we are not going to use BLE, and then the first thing is that we were kind of bounded with the hardware that we managed to obtain, because from the beginning, we wanted to reach a real world application, so to take it and implement it. So we managed to achieve this a very nice wireless BMS nodes, which have this Texas Instrument microcontroller, where Texas Instrument does have a BLE implementation, but this BLE implementation, from the best of my knowledge, did not accept more than 8 nodes. And in fact, my advisor, Samuel Kregu, before my PhD project, he has already made an internship with another person where they have evaluated this BLE idea, and they have found the same problem of going to create a network with more than 8 slaves. So this was like the main reason why we discard Bluetooth Low Energy at the beginning. Then when we start like going a little bit deeper into this technology, I felt that it would be like kind of hard to ensure the bonded latency requirement with this technology. But that is what I understood from the outside. Maybe you are kind of an expert in BLE from my point of view.
No, I don't see anything bad in the path you went. Actually, I think it's a great solution. I was just wondering, yeah, the rationale behind your choice, and what you say is absolutely valid.
Yeah,
perhaps that maybe something which is even more fundamental is that if you want to be BLE compliant, the smallest connection interval you can choose is 7.5 milliseconds. In my best understanding, this is not enough for you. This is probably the strongest reason I would actually bring forward for using something else like you did.
Okay. Yeah, it was kind of, I felt that I will not have like a lot of flexibility using Bluetooth Low Energy. So
no, that is absolutely right. So I actually perceive that the biggest limitation you would have is really the connection interval, because the lowest amount is 7.5 milliseconds, and you actually want a very tight communication. So yeah, this makes sense. Okay. Good. The second question I would have is about the scalability of your solution. So actually you mentioned in your thesis that you're using the GAC, which is a very nice feature, but I was wondering if you can discuss a bit the limits. So how many devices can you support? Is the problem if you have a bigger card and there goes away, or can you just maybe discuss a little bit?
Yeah. So here we have like the scheduling function for the network, where we have like the complete picture of what we have it. From my experiment results, only when the network was in this environment with very high interference, only at this point the network was required to use all of the retransmission time instance to keep the high reliability characteristic. So in a normal environment, and for the wireless BMS, which is inside this vehicle and is kind of more robust to external interference, with this 100 milliseconds interval, I would say that the network would be able to support like 2 or 3 nodes in addition at most. Yeah. If you want to, of course, the group back knowledge can be adapted to much more nodes, but we will not be able to meet the 100 milliseconds with one central device. So if we increase the number of nodes, I think that with a number higher than 15 nodes, we will need to set a longest time refresh requirement than 100 milliseconds. With one central device, we might arrange some kind of thing to maybe have another central device, but it would be like to create another network, which I don't know. Just this. If we want like to keep the 100 milliseconds, I don't see how we will have more than 15 nodes. But
so this is already kind of your limit.
Yeah, for this for the 100 milliseconds update refresh time. Yeah.
Actually, you're touching already my next point, which is that in your thesis you wrote that in a typical BMS, I didn't know that, but in a wired one, there is redundancy envisioned. And actually, that's my question for you. So, do you also envision redundancy in the wireless BMS? And if you envision redundancy, does it mean that then you have to significantly reduce number of nodes you can support?
Sorry, if I did not understand the question.
So you mentioned your thesis that in a classical wired BMS, one has redundancy.
Yeah, okay.
Okay. So my question is, now that you have been making a wireless BMS, how would redundancy affect your solution? Because to my understanding, you would have to reduce then the amount of supported nodes.
Yeah, I think that in the redundancy point, actually the dynamic retransmission mechanism adds some kind of redundancy from my understanding, because we give to each node like multiple transmission opportunities. Another solution for this kind of redundancy thing would be to actually put another central device or a second radio interface to the central device, which will receive like in parallel maybe not in parallel, but like in another radio frequency channel at the same time, and you measure from the nodes every 100 milliseconds. So this will be some kind of solution for this redundancy problem.
And do you happen to know in a real world BMS how much redundancy is needed? Because actually I'm not an expert on BMS, and I was just wondering how much redundancy is needed or expected.
Yeah, I feel from the discussion that I managed to have with the BMS team and with my advisors, I feel that we are not required to have that much redundancy in addition to the retransmissions. So to have a second central device would be very good, because you will have actually the redundancy guarantee, but you will also increase the cost of the solution. And as we discussed this morning with Samuel, in the automotive industry, the cost is the leader. So we try to always make that cheaper, but with something that should work. Yeah. So it is.
Sounds good. So actually, I have another question. This now brings me to slide 69.
Mm-hmm.
And here, so you did mention that, I mean, exactly, that security is not really a problem, because indeed the 5.4 standard does foresee many features there. However, I would like to challenge you here a bit, because there is no problem, yes, but as far as I know, the use of encryption, for example, requires at least 14 bytes longer payloads, right? Mm-hmm. And you are already playing with a very tight timing that you're trying to maximize the payload to make sure that you fit everything. Yeah. So can you discuss this maybe a bit?
Yeah, for the payload point of view, particularly in this system, we have a maximum payload size of 256 bytes, which is actually much more than the required by the wireless BMS, because our maximum payload today, even with the state of charge report and the voltage and temperature, it's around 60 bytes. So in this case we are good if the system has this length of maximum payload. But otherwise, I agree that it could be a very big problem here.
Okay, but if you think that you have been already well provisioning to 255 and you're just at 60, I mean, then of course there is room for, there's quite some room for increasing, I mean, having some overhead for encryption. Yeah. Okay, then I get that. I'm not sure how much time I have, so I just ask you, just interrupt me whenever.
This is fine, I guess. It's more like how many questions you are leaving for the other jury members.
Exactly. Perhaps I can make a last one, and then we can kind of move forward.
Okay. So. Go ahead. So I understand you finished, or you want to go ahead?
I mean, I will have a last one unless there is another round afterwards.
Okay. No, you can go ahead and
Maybe
ask a
one
question.
So my last question will actually be about interference. I mean, that's probably not surprising given my background. So you actually have made a design choice, which is that you do not execute CCA. So you don't make a clear channel assessment at the beginning of the time slot because you say there is no internal interference. And therefore, this makes sense to basically save the few microseconds for this clear channel assessment check. And my question is, does it really pay off, or did you try? If it was enabled, by how much did you help mitigating external interference?
Okay. When I received the TSH implementation from Texas Instrument, they already have defined this 3.3 milliseconds time slot, and they have left like this space at the beginning for the clear channel assessment. Yeah. From my point of view, I never tried to use this mechanism, but what I can say is that I decided to delete these few microseconds at the beginning of the time slot because I had many problems with the TSH implementation, because sometimes my nodes just lose synchronization of the master who was not able to complete their task in these 3.3 milliseconds. So I didn't want to increase the time slot length, because I wanted to have the more possible time slot in this 100 milliseconds time interval. So I just decided to reduce these few microseconds at the beginning, which would make it impossible to execute the clear channel assessment. But from my point of view, I never thought to execute this because I have like a decentralized scheduling feature which already ensures to not have as much as interference. But this is like my...
Yeah, I mean, the only two interesting kind of features I noticed that you just excluded it like a priori, which is okay, but I just wanted to see if by any chance you made some measurements, if there is any difference. And the second choice that you made was that you make the deny listing on the master,
Yeah.
and not on the slave. So not on the peripheral, we do it on the central, not on the peripheral. And one of the questions I have is, could this be a problem? Because sometimes the slave, especially if you have a large car, may be located closer to the interference source.
Yeah, I feel that maybe it would be a problem if we have used a different network topology. Because I feel that with the star topology, which before decided to use a star topology, we need to guarantee that we actually manage to reach all the slaves with a reasonable good receive signal strength. So I decided to make it in the central device because he has like the whole picture of the network, and if I made it in this central device, I will be able to addition this deny list mechanism without interfering with the network operation or without creating additional data transfer in order to check if everything was okay or not. So it was just because it was I felt that it was more convenient to do this in this way.
All right, so thank you very much. I will then pass on the token.
Thanks to you.
Thank you very much. So I will leave the floor now to Thomas. So enjoy.
Thank you. Thank you. Right, Fabian, fantastic presentation. Thank you so much. Great joy reading your dissertation. Super clear, cool work, very close to what I'm doing. So I believe I understand everything that you did, and it's very impressive work. I like very much the novelty of what you propose, the group back stuff, the channel hopping stuff, the synchronization of the modes only. That's quite cool. And then also, of course, your hands-on approach. As you know, I love seeing boards that blink. It's perfect.
Thank you.
I have 33 questions that I wrote down, but I will ask 3.
Okay.
Is that okay? And then over a drink later on, we can ask more of them. I have so many questions, clarifying questions. I would like to make sure that I leave some for the other members of the jury. So I will on purpose kind of ask pretty specific questions, just jumping into some technical details, you know, I like that.
Okay.
The first one is, if you go back to slide 30,
Okay.
can you talk to us a little bit about what happens when you lose a group ACK? When you lose both group ACKs?
Okay. First of all, it was a really big concern for me.
Okay.
Because at the beginning I have only one group acknowledge mechanism, and the network did not work out really good. So the initial version of course, as you know, we have many evolutions of the system. So at the beginning I have only one group acknowledge and it didn't work. So then I decided to use a second group acknowledge time slot, which, as you can see, is a, I don't know if you can see it, but it is a shared
Yeah.
time
I
slot.
remember I read it, but it's
Okay. So I use it like this time window that I have, like kind of free to have a kind of redundancy. So there the probability to lose a group acknowledge is kind of low. But if, for example, if we lose one message from one node, and then we lose both group acknowledge, if the nodes did not receive a group acknowledge, maybe I have to detail that in the manuscript, but if the nodes did not receive the group acknowledge in both time slots, they will keep listening to each time slot until receiving a group acknowledge. And in the central device side, if it does not, it is actually predefined to send another group acknowledge once it was posted.
So you keep listening, you receive another group acknowledge where your name appears, and you say, oh no, I did not send again, so you send it.
Yeah.
So you kind of catch on.
That is pretty much the approach that I have.
I did not see this in the thesis, and it kind of stuck with me, like, how does this work? But
Yeah, you're right. I did not put it in the thesis.
very clear. If you go to slide 54, I like the fact that you're not switching through a million slides, but you just go straight to the slides, and I like that a lot. I'm very surprised that you never get above 400.
Yeah, me too.
Okay, because is that whisker the max and the min value?
Yeah. In fact,
because you can, I mean, as you explained correctly, depending on when you wake up, it's either right after or right before, kind of worst and best case. But the worst case is that you don't receive multiple in a row. So I expect to see a couple of 400s, 500s, 600s.
yeah.
Why is it?
And this is, I thought about this, and for this reason I chose the T-syncon for 100 milliseconds. So in order to have like two opportunities to receive the wake-up interruption if the nodes lose the first wake-up interruption. So we have like 100 milliseconds to receive the wake-up interruption. And I was actually expecting this to happen. But in the experiments that I did in the battery pack at the laboratory, I did not get this, and I repeat this experiment multiple times. But of course, I feel that if I repeat the experiment today that the network is in the vehicle, I will certainly obtain these cases where we have the wake-up time higher than 400 milliseconds. You are absolutely right there.
And could it be that your 100 number is not statistically, how do you say that? It's not enough, basically?
Maybe.
Okay. So if you did it 1,000 times, you bump into a case where you lose.
Yeah, I feel that, of course, the probability to go higher than 400 milliseconds, it's more than zero. It's not zero. So I feel that, yeah, you're right. I should have thought to make more wake-up procedures.
Yeah.
But I repeated the experiments multiple times. So
No,
yeah.
that's fine. I mean, understood. We understand.
yeah. But the point is that you are right, actually.
Okay. I did some back of the envelope calculation of this 60 microamp number. So it's a 15 milliamps when you transmit. You wake up twice per 100 milliseconds. So let's say that is 2 milliseconds of wake up time. Per 400 milliseconds. That's 0.05, 0.50% of your duty cycle, I calculate 75 micrograms. So maybe my 1 millisecond is a bit too conservative, so it's about that. So I get the same number as you get at, within a couple of percent. So it's
Okay.
So it's good. It's good.
Because I was a little bit lost.
No worries, no worries. Now have another question about. I was very, very excited at reading about your synchronization thing. So if you go to slide 48, it's 48. Yeah.
Here.
So sorry, the next one, 49, the one where with your approach.
Here.
Yeah. Yeah. Okay, so because the master is on the 12-volt battery, you don't want it to consume anything.
Anything.
Anything, okay. And so you let the network kind of stay synchronized together, and then you reattach to it whenever you need to. Okay, great. But aren't you, because the network is running in such a kind of an automated kind of completely, all the nodes are the same, isn't there a case where you could form a 2 cliques or 3 cliques of synchronization, like where in your case you have 4 nodes that two pairs of nodes stay synchronized but never hear the other ones and start drifting, and you end up having half a battery back here and half a battery back there. Is that possible? Because you don't have a time master.
Yeah, it is possible.
Okay.
But it never happened because the main principle is that all of the nodes have the same synchronization always. So at each time the time drift would be reduced to 0 each 400 milliseconds. And even if you do not listen a synchronization beacon, you will still in the guard time, and you are actually.
Sorry, how much is your guard time?
300 microseconds.
Okay, so that's, and your drift
That is something like 4 seconds. So in order to do synchronization, you will
4 seconds.
like 4 seconds, and we are sending beacons like all over the battery pack.
But it's so if let's say that we have the left nodes and the right nodes. If the left nodes do not hear the right nodes for 4 seconds, so my situation is the left nodes are synchronized together. They hear each other every time.
Yeah.
The right nodes hear each other every time, but there's a boundary that causes those 2 pairs not to hear each other for 4 seconds.
Yeah, because
In that case, they will just disconnect.
yes, it may happen, but if we have like 6 nodes in one side, and then we have 6 nodes in the other side. So every 400 milliseconds. So if you don't listen to the other ones, yes, you can create actually isolated networks in both sides, which would be a problem. But in the conditions that I test the network, we are actually capable to listen from the other side of the network. And I don't know, maybe you have read about it because you saw my manuscript, but I create another version for this sleep mode, which is something that achieves a lower energy consumption, where sometimes I did not send the synchronization beacon, and then to design this reduced mode, I test like different configurations, and this phenomena that you mentioned actually happened. So I ended up with like 3 different networks with different synchronization, and at the end, when the master wanted to resynchronize, it only got like a part of the network and the other ones not. So this mode is kind of maybe risky for this point of view, but it depends on the environment. Because in my case, in our case for the Renault Zoe, the nodes were actually capable to communicate from one side to the other one.
Yeah, but I mean, I agree, but I don't agree. If I buy a Renault Zoe, 15 years from now, I still have it, right? I will use it for 15 years.
Okay.
This goes on 90% of the time. So after 15 years, for sure it will happen.
Okay.
And because you don't have any recovery mechanism, you go back to Renault. You say, my car is dead.
Yeah, but actually the recovery mechanism is easy to implement.
Okay.
And I actually implemented it Not
how did you do it? How did you
but
do it?
not because I wanted, because I had to.
Okay. So you bumped into the problem. and
No,
you had
but
to-
I not bumped into the problem because of this,
Mhm.
but because when we put the battery pack inside the vehicle, for some reason we have the sleep mode command that we used to put the network into sleep mode. It was a CAN message, which was also sent by another calculator in the network. And then I start doing this calculator sent this message, and my network goes to sleep mode, and then I didn't understood what had happened, and I put it in active mode, but then the system again in sleep mode. I ended up with my master completely out of synchronization of the network, and with multiple networks. So I had to create like a special mode for the master. This is not like a very good implementation, but it was a user recovery mode in this case, because I was very sad because my prototype didn't work, where it just tried to wake up and it's joined to one network. So then I updated the firmware of these nodes to instruct them to never go to sleep mode again. So then I put my master again in a sleep mode. And then I wake up again. And in this way, I managed to recuperate all of my nodes without unmounting the battery pack from the vehicle.
Very cool.
So I agree that the final system should have some kind of mechanism like this one, because you are right. In 15 years, it will happen. So.
And you found out for some weird reason it happened, but you kind of on the fly sitting next to the car, you kind of recovered that system, and not in a super clean way, but you understand how to do it if you had to.
Yeah. I understood how to do it, and and actually the test that I made to test if the network was accessible from the outside, that I use a master in different positions, it was an accident actually, and it was this accident because I found out that with an external master I managed to update it and then update the nodes from the outside of the battery pack, and then I said, maybe I can make this experiment and put the master in different positions to show this kind of results. It was a happy accident. At the moment, it was not happy, but
Yeah.
it was. I had some cool results from this little inconvenience.
Very cool, very cool. Which brings me to my third question. It is your, so I would like to understand a little bit better what your contribution is, what you did. I mean, clearly you did a whole lot, but I'd like to understand how much of the network you implemented or you had to implement, how much you were involved in that, so that we're all 100% convinced that you just master everything like that. So can you talk about what you use and what you?
Okay, can I show you? I actually prepared some slides for this because I agree that in the manuscript it is not at all clear what I received and what I have to implement to reach my. Because this one was more like an engineering part and not much like a research thing.
Yeah, but
Yeah, but
the best engineer, the best
So,
research is the best engineer.
I have this last, which is behind the scenes where you might have.
Okay, great. Let's go.
So, at the beginning, I received this system from Texas Instruments, which is a classic IoT protocol stack, which was ready to work in the CC2652 microcontroller, which was very convenient because I tried to use Contiki NG or OpenWSN in this microcontroller, and they were not at the time adapted to this platform, and I didn't wanted to spend a lot of time like trying to find some way to implement the network. So I received this one, where we have the nodes, the central device, but the central device only had implemented the BLE physical layer and the TACH. Just a little parenthesis here. This was a happy coincidence that they were already using the really physical layer with the TSCH MAC, because it means that we have reached to the same conclusion to use this physical layer with the TSCH MAC protocol. So it was actually really useful. And then the master uses a Linux gateway to manage the network. So I took this and I removed all of this part, and at the end I ended up with the BLE physical layer and the TSCH layer. And on top of that, I create a wireless BMS application for the central device and the node.
Running on the CC.
Yeah, running on this platform.
So on one core you have the black code, and on the other core you have the blue node. It's a dual core system.
No.
No?
No, it's a single core system.
Okay.
It has a little microcontroller for the radio management, which is like the very low radio interface. But okay, so I have this, which was very classic, and I managed to create a network with a fixed schedule. And the TSCH implementation was already working with that fixed scheduling function, and the time slot was already 3.3 milliseconds. I have to modify it a little bit, but it's another story. But then I start with my dynamic scheduling idea. Okay, I have like a PC with a Python script to flip the data and the statistics of the network. Okay, but then I start to implement this group acknowledge dynamic retransmission scheduling function in the TSCH network implementation of Texas Instrument, and I found that this TSCH implementation was not ready to work with a dynamic scheduling function, because actually this scheduling function changed within the same slot frame. So it received a message and then it has to adapt instantly. So it was really hard because I didn't have like a proper documentation of the network. So I have to read like hundreds and hundreds of lines of code to understand how it works, and where I have to change the TSCH layer in order to get this group acknowledge to work. And these were really like a couple of months that I used to this one.
Yeah, I am convinced.
Then on top of this, it was like, okay, we have something that works, and we have to start developing the other parts of our solution. So I put the ASIC drivers in the wireless BMS application, where it was a lot of work also. And then with this, we have the active mode of the network. So we had to implement the sleep mode, the scheduling function, which was, again, I need to change completely the way of how the network worked, because it was supposed to have a central device. And now I delete this central device, and the nodes will be capable to send synchronization beacons and then receive these beacons and identify if this beacon was for the central device or not. Okay. So here it was again my implementation, and on top of under this I put the channel denial list mechanism, which here it was more easier because I already had prepared my solution to do this. So to this point I made like a lot of work trying to make a lot of real-time calculations, because it was the big challenge was this one, to be able to execute the calculations in the good time intervals and to have something that works. Because at that time we had like the COVID thing, so I was able to go to the lab like one time per week. So I set up my network, and I leave it like working, and I came to the next week to find that my network stopped like one day after that for any reason. And and then I continued to develop. When we wanted to go to the vehicle, I have to add the CAN interface, which is this transceiver, which is on top of the master, where I have to adapt all of my messages to this CAN interface, and at the same time adapt my Python script thing. And then okay, the CAN interface, and then I added like the beyond wireless BMS, so the state of charge algorithms, and I made something also around the balancing compensation. You have saw it in the manuscript. And that was pretty much it. I developed this graphical user interface for the demo purposes and to make it like beautiful. But the Python script in the background is like use a console application, which is kind of ugly, I would say. But
yeah, okay. Thanks for creating those slides. This is very clear and very clearly excellent, excellent work. And I don't want to say engineering work because this is what it's all about, right?
yeah,
Having an idea, it's 1 minute under the shower, right? But this is the real work, and this is absolutely part of your PhD. So don't dismiss it as being, oh, it's just engineering. Right? Which brings me to my last question. Maybe you told us already, probably you did. What is the hardest thing that you did? Like, what is the thing that it just went on and it didn't work, and you somehow found it? Like, what is the biggest problem you faced? And you don't have to disclose anything that you don't want to disclose. I just want to have you talk about a problem and how you fixed it.
the main thing, it's difficult to find one single thing. I would like to say two principal things, which are the core of my PhD thesis. The dynamic retransmission was really hard to implement. So when I actually managed to prove that my network was doing dynamically at each slot frame something different according to the needs of the network, and then that we managed to execute like multiple retransmission and everything worked very good, it was amazing. Because I made like a lot of tests. Even the night I let my network, and next time in the morning I wake up and I saw like, it does not work, and I had to find why. The other one was the sleep mode. This thing of just turning off the central device, it was not easy. It was not easy because I had to change the complete network implementation actually to make it work and to add some new features that I will not. It was not supposed to work like in this way. So when this thing worked, it was really nice. So.
And would you sorry, I cannot stop. Now that you did all of this, wouldn't it have been simpler to start from a pure radio driver and do everything yourself?
I tried.
Because what I'm hearing is that you got some code, hundreds of lines of code, that you had to first understand and then completely destroy and rebuild anyway. So just to be a bit provocative, right? Wouldn't it have been simpler to have a data sheet and just a bunch of registers?
Yes and no, because at the beginning we were trying to figure out how to have a TSCH network implementation for this microcontroller that we were able to change completely, And then we did not have like an immediate response from Texas Instruments, so I have like some time to try by myself to check if Contiki and Gmake works, to OpenWSN maybe. But then I said, okay, maybe if I implement it by myself, it will be like a good idea. But then I found it so hard. At that point, I said like this will take me like ages to implement. No, to have a network that works without failure, it will take me like a lot of time, and I did not want it to spend like a big part of my PhD project trying to make it work.
Okay.
If I did not receive the TSCH part from Texas, I would be obligated to do it. But because we received it, we said, okay, it works now. So, but of course, it was a lot of work too. So.
Yeah, super interesting. Thank you. I yield the floor. Thank you for your answers.
Thank you.
So, thank you, Thomas. I would like to ask Michael if he could go on and find some nice questions. Can we hear you?
Okay, we don't hear you. 1 second.
Yeah, muted as well.
No, it works.
Yes.
It's okay.
I hope you can hear me loud and clear.
Yeah.
So, great. First of all, thanks for a very nice presentation. I really enjoyed it. and I think you have done a really nice piece of work. And I also think it's nice to see when PhD students also do practical work, not only theoretical work. You have done the complete change, so to speak, from, let's say, more pure academic things, but then you actually have implemented, and as you have discovered, there are a lot of problems that occurs during the implementation that you don't foresee in the beginning. Life is not that easy as it is only when you do some fancy equations and say, well, this will work, you see it's a huge gain or something like that. But several of the questions I have has already been asked by Thomas and Carlo, but I have a few more, let's say, general questions. And if we start from the beginning, already when you started this work, and I assume there is some kind of requirements coming from the company, so to speak, when it comes to, okay, what is the battery lifetime? How long should it last for? Is the reliability really needed that high, or the latency requirement is the most important thing? Could you elaborate upon this? I mean, how do you carve out the real requirements, so to speak?
Okay, yeah. Actually, we had, at the beginning of the project, the real challenge was to identify the requirements of our system. And because, of course, we are like doing something new, it was not as easy as just go and check if how some other people do it, and then we are going to do it in the same way or better. So we took some requirements for the classic BMS, as in particular the latency. So the classic BMS has this 100 milliseconds latency. Not because the voltage from battery cells will change significantly from 1 second to another, but it is more related to some safety issues. So it's because we are obligated to retrieve diagnostic data every 100 milliseconds to be prepared to react as soon as possible when something goes wrong. Yeah, that was the main. It was the more like the more fundamented requirement of our system, the latency, 100 milliseconds. Then for the reliability, we wanted to reach the highest possible. The highest possible, it would be nice. Because again, for these safety problems, we needed to receive all of the messages every 100 milliseconds. So this is a basic requirement of the BMS. The most difficult requirement to set was the energy consumption, to be honest. Because we didn't have like a reference in the market to see, okay, this thing should consume like less than 1 milliamps or in active mode and less than 70 microamps in a sleep mode. So for the active mode, we decided to go with a very small value compared to the energy consumption of the BMS ASIC, which it was around, depends on the ASIC, but it is between 10 and 15 microamps. And for the sleep mode, we went just in the state of the art or low power networks and check which would be a reasonable value that it would be possible to obtain, but respecting the 1 second wake up limit. That again, this one was get from the BMS requirements.
Okay. I mean, when you did the choice either by running with this wireless I/O or Play or something like that, you somewhat restricted yourself to the 2.4 gigahertz. Was there any discussion of using some other frequency bands, or was it more like the okay, there's a lot of chipsets available for 2.4, so let's go with that due to low cost or something like that? Or could it have been other frequency band with less interference?
Yeah. For this, we wanted to use some, of course, some open spectrum. So it will be, if I'm not wrong, 2.4 gigahertz or the sub gigahertz, like 800 megahertz, depending on the country. So in the 800, we have some technologies like LoRa, which do not have like a high data rate, but they are designed for long ranges, from my understanding. And we wanted to keep, it was very interesting to keep like the electromagnetic signals inside our battery pack. So for this reason, and again for our choice in the microcontrollers, we wanted to use the 2.4 gigahertz band. But before, we already have discarded some technologies like LoRaWAN for the data rate and the payload size, and again because they are not designed. I feel that they are not designed for this kind of short range networks.
No, I mean, that's true, but I mean, it might be some other technologies that could be looking for. But I was thinking a little bit, now when I see this slide, you have the blue low energy physical layer. Could you just update me a little bit? Are there any forward error correcting codes included in that one? Or is it just plain CLC?
It does have, no, it does not have any kind of forward error correction. No, it is possible to detect some kind of error in the transmission with a CRC, classical approach,
Yeah.
but forward error correction, as in the 802.15.4 standard, no, it really you send it into, well, when you use the 2 megabit per second data rate, because BLE proposed some coded options, but in this case, in this particular case, we use the 2 megabits per second data rate without any kind of forward error correction.
Yeah. And then it comes to a little bit of speculation then. Since you do retransmissions in a system, would it make sense to add a very simple forward error correcting code to improve the reliability and still stay within the latency bounds that you require?
Yeah, I actually, in fact, prior to my PhD project, I did my master internship. It was already around this wireless BMS system. And in this case, I tried to use the 802.15.4 physical layer, which has this kind of forward error correction. And I found a limit in the maximum data rate and the minimum time slot length that we can achieve with this physical layer. So my conclusion, or the main conclusion from this internship, was that I had to increase the data rate. It was some kind of mandatory if I wanted to reach or to implement a network with more nodes. So at the beginning of the PhD project, we decided I preferred to go with the BLE physical layer instead of this one with forward error correction.
Yeah. Okay. So the other thing, since I've been working with wireless IU many years back at ABB, and so I also, what we discovered during that time, sometimes we said it's better, instead of doing retransmission, it's better to take a new sample with the latest fresh value. What is your stake on that claim?
Yeah, at the beginning, when the first version of my system, at that point we send it only one measure every 100 milliseconds, and this measure was taken just before the transmission time slot, and I left it like this way. If I had to do a retransmission, I kept the same value. because again, the voltage data in this application will not change a lot within 50 milliseconds of time interval. So I just considered that it was okay to send the same value without measuring a new fresh value. But I totally agree that if we have, like, for example, if we include in our network the current sensor, which is a variable that changes a lot over time, it would be better to send at each time, even if in the retransmission, a fresh value to the central device of the wireless BMS.
Yeah. Okay, I have only two more questions, and the next question I have is basically, I think it was on your last slide, you had these challenges, and you're also been discussing the security, and in the middle you have safety, and yeah, safety for the system, and you pointed out, yeah, this one, hardware problems, and I have a question because I don't know. I only know that in other domains, for instance, if you're working, let's say you're deploying a wireless system on an oil rig, which is also have the highest safety integrity level, there are constraints on how much transmission power you're allowed to have, because it can create explosions and so on, and you need to really hack the gateway and the nodes in really fast, so to speak. So are there some requirements in BBMS for TX output or something like that? Because I mean, if there are constraints, you need to lower the output power, and of course you have implications on your results as well. I'm just curious because I don't know.
Yeah, okay. At this point and during my PhD project, we had never had this in consideration, because at this point there is not a regulation that requires us to limit the output power inside the battery pack. We have the typical regulations so in this 2.4 gigahertz band for this kind of devices, but we don't have any particular regulations for the wireless BMS at this point. Maybe if many vehicles start to implement this kind of system, we will have more regulation around this, because today there is not common to have wireless network inside this kind of system. So to be honest, we never put these questions in our discussions during the project, actually.
I was just curious because you never know what is the safety and integrity level requirements are for certain applications, and of course that impact on the results. So then we come to my final question. You have done PhD studies for 3 years now.
Yeah.
So the question is there anything that, with the knowledge you have today, is there anything you would have done differently if you should have started today?
Oh, that's a tricky question. I would say that, for example, this is just kind of an implementation thing, and I would prefer to have the CAN interface of my system at the very beginning, and not having to adapt my whole system, which was already working, to this CAN interface, because I had to modify a lot of things that I think that it would be perfectly, I would be able to avoid this if I would have this thought at the beginning of the project. But for the other choices that I made during the project, I am actually very, very happy with them, and I will not change anything else here, at least for this project, no. Maybe I would like to have started in another year without the COVID because I missed like the conference in presence, but it's okay.
Okay, thank you very much.
Thanks to you.
Good work.
Thank you very much. Yeah. I would like to maybe invite the two other members of this jury that I didn't introduce, so I'm really sorry, which are Patrick Bastard, Directeur de Recherche at Renault Group, and Xiaoting Liu, which is a fellow and director of IoT Lab at Texas Instruments. So I would be happy if you could maybe have some questions for him. So maybe Xiaolin, sorry.
Can you hear me?
Yes.
All right, thank you. First of all, thanks Nicola and Fabian for inviting me to this meeting. It is I know this is a long journey. We started about 3 years ago, and I'm very happy to see actually you're able to show the data, which is 99.993% of the reliability out of the real deployment in the field with Renault Zoe. That itself is a huge accomplishment in my opinion. I don't have too many questions, but maybe two. One is because I think one of the reasons we selected TSCH and also as Texas Instruments selected TSCH is because it offered a lot of knobs to tune the network performance through, for example, frequency diversity, right, channel hopping, time diversity, time slot, and also actually space diversity, which is the mesh capability. And we talked a lot about redundancy, blacklisting channels. So I would like to ask the question, since you have so many knobs during the whole engineering process and also research process, what is your read out of this whole knobs? So which one you think is most effective? Which one is less effective? Do you have any thought or study in those trade-off? I think everything's about trade-off. We understand the engineering process. So would like to get your first-hand feedback on that.
Yeah, okay. When I decided the network the topology of my network, we have like this star topology or mesh topology options, and then we just made a test where I measured the received signal strength from the central device from all the nodes, because we wanted to make sure that this central device was capable to communicate with a good in good conditions with all of the nodes. If this test would have a different result, I think that we have to go with the mesh topology network, which will increase the complexity of the system considerably, I think. So it was this kind of trade-off between if our network architecture would be different, so our battery, for example, had like other kind of architecture, and the nodes were like more high in the vehicle, we will be able to implement a mesh topology. So these choices was made more according to the environment that we had in the Renault Zoe battery pack, and in most of the battery packs that we have today in the electric vehicles. This was pretty much the consideration that we had when we were talking about the topology of the network.
Okay, thank you. The second question is related with your sleep mode, the call management. As we know, the reason we want to cap the synchronization because it's a centralized, totally synchronous network. And the reason we have to wake up periodically is because of the clock drift, right? And as much as I know for TSCH protocol, during the sleep mode, you're running, assume all the devices are running through the real-time clock, which is the 32 kilohertz. And it needs to be guaranteed the 32 kilohertz clock has to be meeting 20 ppm requirement. So have you studied the clock accuracy relationship versus network overhead for the synchronization? Again, it's another trade-off between the clock accuracy. For example, your clock can reach 10 ppm accuracy. How much is saved the power from the network synchronization perspective? Have you studied the area in this
Yeah.
context?
Actually, in my manuscript, so this is like a diagram of the sleep mode that I explained today, where every node resynchronizes its clock every T-sync. And when I implemented another sleep mode, which was an evolution of this one that achieved lower energy consumption, because I saw here that actually with the guard time that I have choice, that actually Texas Instruments have choice. With the guard time that we had, we were not obligated to resynchronize the clocks every 400 milliseconds. So I make another implementation where the nodes were still sending a beacon every 400 milliseconds to keep the wake up time requirement, but they only synchronize its clock every 1.6 seconds, which is half the maximum interval that they are required to resynchronize. When we take in mind a clock drift of 40 ppm, yeah. So I do study this, but for this new evolution of the sleep mode, and with this I managed to execute several tests, and this actually works. And the network managed to keep the synchronization for several weeks with these values for guard time and this. So this one was the study that I made around the clock drift and the synchronization interval in the sleep mode. Yes.
Thank you. My last question is about reliability again. As we know, the payload size, the smaller it gets, right? Or less traffic for the network, and it's going to be a lot more robust. And when you try to dump a large amount of data into the network. And I know I'm very excited to see when you apply some average computing, you're already able to dramatically increase the network performance. But have you thought about if you do have a neural network engine in the CC device? Of course, back 3 years ago, we don't have it, but now we have it. And if you start to thinking about we're sending a lot of redundant data when we do every 100 millisecond duty cycle, maybe similar data is being transmitted again. So instead of doing that, if we identify some markers, let's call it voltage variation of the health markers, and you only transmit, you do that neural network inside the node and then only transmit those markers that you detected. Have you done anything in that area?
I did not consider any kind of neural work in this implementation, but I actually admit that it would be very interesting to have in some kind of these systems that which would be possible for the voltage and temperature data, I think, but maybe for the diagnostic data for safety reasons it will not be possible. But I think that actually this is a very nice idea for a possible evolution on the wireless BMS application actually.
So maybe I'll take this opportunity to do some advertisement. We do have a very tiny, we call it tiny neural network for the CC device available. Of course, it's not in the production yet, but definitely open for further collaboration in this area, because truly believe you should get the best of the network reliability when you only transmit the information that's absolutely needed. Thank you.
Okay.
And excellent work. Congratulations.
Thank you. Thank you so much.
Thank you very much, Sherry. So maybe Patrick?
Yes, hello. Thank you. First of all, thank you very much for the very nice presentation and very nice work that you presented today, which is valuable from both points of view. I mean, from a purely technology and scientific point of view, but also from an industrial point of view. So I think it's worth mentioning that you managed these two sides of your work in a very good manner. So thank you very much again. I have one question which is about safety, because as you know, the BMS is really at the heart of the safety of the battery. So this is not the only safety barrier in our safety concept. We have other safety barrier, of course, but it's really key in the safety concept of the battery. So I wonder if you try to make a clear demonstration that the ASIL D, as defined by the ISO 26262, can be reached, or should we take some specific measures in order to keep ASIL D level, which is the case today in our cars with wired BMS, and does wireless technology has an influence on the fact that we keep the ASIL D level of safety regarding the BMS, or is it absolutely manageable?
Okay. We do have many discussions around how to reach the ASIL D level in the wireless BMS. And then at this point, this radio frequency microcontroller is not ASIL D capable. It's not ASIL D capable. So it means that the things that we are doing today of making these computing activities in the nodes, this will not meet the requirements to achieve an ASIL D system. Yeah. So the approach that some providers on the wireless BMS have chose is to just do not execute any kind of operations inside this radio frequency microcontroller, and only use it as a transmission medium, transmission channel, in order to send the data from the BMS ASIC, which is ASIL D capable, to the central BMS, which is also ASIL D capable. So that's why we put this item in the open questions for around the wireless BMS, because it is not very clear how we will manage to achieve an ASIL D system where we are able to make these calculations in the radio frequency microcontroller without having to add some more robust microprocessors, which will increase the cost of the system. So this is what this was pretty much the discussion that we had around how to achieve the ASIL D level in this wireless BMS system.
Okay, understood. Thank you for your clear answer. My second question, and that will be the last one, because you already had to answer some of the questions. So my last question is about the number and the type of data that you can collect through the wireless connection. I mean, today, as you explained, we mainly deal with conventional data, like the temperature, the voltage, and so on. Maybe in the future, for some reasons, we will have additional data available inside the cell of the battery itself. For example, if you have some gas generation today, it's very difficult to measure the gas generation inside the cell, but it would be very interesting because gas generation can be directly linked with the aging of the chemistry of the cell, and you could that way anticipate some bad event, let us say, that could occur in the heart of the battery. So, I mean, is wireless technology, is it a kind of enabler in order to consider additional data and more data? Because you do not have to wire anymore the connection between the master and the slave. So it could be an enabler to consider more data. Of course, assuming that you have the sensors which are able to collect this data for sure. But I was wondering how far wireless could help us also to consider more and more data inside the battery in order to better monitor the battery itself.
Yeah, actually, I totally agree with you. And the main reason why we leave this the maximum payload of our network to 250 bytes was exactly the reason that you just described it, and is that we wanted to leave the door open for future new applications or new functionalities inside the BMS that the inclusion of the wireless link will bring. Because we will, in particular, it will be easier for us to just reduce the maximum payload to only the data that we needed to send at the moment, which was like 60 bytes, and then reduce the time slot length and have more retransmission opportunities and have like a higher robustness of our system. But we do really wanted to leave this maximum payload size to this big value in order to enable more, new characteristics on the wireless BMS.
Okay, so thank you very much. Thank you for your presentation again. And, well, that's all from me. Thank you very much.
Thank you so much, Patrick.
So thank you very much. So I'm ready to ask two last questions. So I'll try to stick to two because you already answered a lot of questions. But before that, I would like to congratulate you for your talk, which was very clear, very pedagogical, really nice to. And you really managed to show the width and the breadth of your work, going from designing a protocol based on good literature review and going straight to really a real life experiment, which is not always possible. And I think I really congratulations for this.
Thank you so much.
So two questions. The first one is maybe related to your dynamic slot allocation. So I like this idea, and I've been thinking you are able to do dynamic slot allocation for the retransmissions, and on the other side you are learning the packet delivery ratio for your channel blacklisting. Okay, so whenever you are ready for giving a new schedule for retransmission, you have an idea of what are the channels that will be used in the upcoming slots, correct? You know how good they are because you know their packet delivery ratio.
Okay.
So what could you? I was wondering whether you could not leverage that information to have an idea of how many slots a node would need to retransmit its data, knowing the channels it has to use.
Okay. It is actually a very good point, because it is true that we have the central device has all this information. It has the packet delivery ratio of all of the radio channels, and it actually knows which channels the nodes are going to use for the retransmissions. To be honest, I never thought about this methodology, but because I always, not always, but I expected to use good channels, which were the best radio channels, and I so to have the lowest probability to have a very low probability to these retransmission messages to be lost. So no, I did not. Actually, it's a very good idea because it will be really great to say, okay, this node is going to use the channel 15 and 14 that have like a kind of. So we may allocate more retransmission time methods to these nodes.
So maybe you don't lose group acknowledgement, another group acknowledgement slot.
Yeah.
That's possible, but maybe as you say, if you select if everything goes well, I don't think it is useful.
Yeah, but the thing is that at the end, the packet delivery ratio is just it's like it's a probability. It's not sure that it's going to work. So if I rely on these estimations to assign the number of time slots, I think that I am less sure that it is going to work. That if I only just give the necessary time slot at each time with the group acknowledge. That's the instant feeling that I have like right now answering the question.
Okay. Another question may be related as well to your channel blacklisting algorithm. You choose a blacklist channel with the constraints of identifying at least min CH good channels.
Yeah.
That was your point. And you choose a min period here by saying I take the best packet delivery ratio and take then an offset saying this is the offset.
Yeah.
That you say to be application specific more or less.
Mm-hmm.
But what happens if your best is bad?
The system is not going to work. But this is the risk that we have. It's not a risk, but this is that we have with wireless communication. So at the end, if you just have a lot of interference in all of the channels, the system is not going to work at all. There is no way. It's like if you put the USB cable in the transmission, so the system, you would just destroy the system basically.
Maybe to go a bit further, what would be that beta to use? That beta, you know? The beta, if you take it, you said you will pick it, and if the value is not bad, but not very, the best value is not extremely good, but it's not extremely bad. So how would you choose the beta, such as not to this fixed value to put it too low, and then you only remove very bad channels, but the other ones you keep, you know?
Yeah, but I actually, this beta value is not fixed. So when the central device executes the evaluation of the nodes with this delta value, and it did not find enough good channels with this consideration, it will update this value, and it will make it like a little bit higher, and then it will do again the evaluation of the channels, and it will repeat this process until it finds the better channels, even if they are not good channels because we are under ultra high external interference. But that's what I thought of the channel.
And then my second question, which is different, is, you know, in avionics world, when you have embedded networks, when you're looking at civil avionics, I'm not talking about military, but civil avionics, you always look at protocols which are totally distributed, because you have stringent safety requirements saying that if one node dies in the system, the full network should still go on. So master-slave configuration is not possible.
Yeah.
Okay. And I was thinking while you were presenting this nice sleep mode, where you remove the master and had a nice round robin around the beaconing node. What if you should think of porting this wireless BMS in the avionics world, which might have some similar settings where all the nodes see each other, have to exchange data, and do some calculation. You showed nicely that the boards you are using for the nodes can do calculations. So I'm not sure whether they can do the same type of calculation that your master has to do, but I think they should be able to, so it seems to me. Yeah, correct. So why not going to something where you have a fully distributed setting, where the beacon for some time is being sent by a master which is on node 1, then it is on node 2, then it is on node 3, to even out this charge of mastering, the same way that you did for the sleep mode, but it should be done for the active mode. So do you see any cons for this solution?
Yeah, I don't understand how in this solution how would we gather the data from the because you're talking in the active mode for the synchronization process or for gating for retrieving the data?
For your active mode, where you're grabbing the data from the others, that the function that you have on your master is on a node. As soon as the node sees everyone, of course.
Yeah, but then how the master or the BMS central computer or the how they will receive all the data coming from the nodes? So which entity is going to receive this data?
You need a gateway, but this gateway is not steering the network. You have a steering network function, which is what your
so it's something that always
that is here to receive the data from the current master, which is rotating among the masters.
In fact, this is some kind of redundancy where, so if I understand well, every node will have like the complete data
for some time
from the device, from all the battery pack.
Do the calculation, the math, and up to some given frequency, push it up in the full system to the main ECU.
Yeah.
I don't know.
To be honest, something like that never crossed to my mind. Today, in particular, for the safety reason. So, with this microcontroller, it is not possible to achieve a safety system with this. But maybe, because I'm not kind of a specialist in safety, but this actually adds some kind of redundancy to the system, and maybe we will manage to meet some
The
kind
idea
of...
is when your master node fails, the current master, the system dies.
Yeah, but in your example, the gateway, it's also a unique gateway, which and this gateway is the entity in charge of transmitting the data, the status of the battery, which is computed in the slaves, to the central computer of the core. Yeah. So if this gateway, we are still in the same architecture. If this gateway just fails, the system is just going to fail. So what we have seen in the state of the art is to use, for example, two masters in the network. So to add a redundancy in the master, where, for example, each node in the net, if you have two masters in the network, and each slave in the node sends 2 times its message in different radio channels, one the first time for this master and the other one for the other master, you already have some kind of redundancy. But then using the others, the slaves in round robin, I that never crossed to my mind, but I...
It was just to challenge you a bit.
Yeah.
So thank you very much. I have no further question.
Thanks to you.
Maybe I'm going to leave the floor to your advisors. I don't know, maybe started with Samuel.
Okay. So I wanted to thank you very much, Fabian, for this good presentation, and of course, moreover, for these years together. It was for me a very good, let's say, journey, or very challenging, because at the beginning of the thesis, I didn't knew where we could arrive, and it's beyond my expectations. I was not very a big expert in, let's say, communications, standards, and so on. And I was much more, I had more competency on BMS. And with this PhD, it was a very good exchanges between the academic world and my knowledge on BMS and industrial knowledge. So it was a very good PhD for me. It was a pleasure to to have you as a student, always happy to hear from some advices, and I think it's something that you have to continue to get always listen to improvements, and it's a good thing you have. I think it's good to keep for you in the future. I want also to thank Texas Instruments because they were very open to this PhD, and they didn't see it as something challenging the industrial part of an electronic supplier, but they were open to give us the hardware, the software, and it was very open mind from TI to this collaboration. And of course, we discussed that it was a very good opportunity not to make all the stuff, software stuff that is not relevant for our PhD. So it was very good to go very on the good topics for this PhD, and it was the main topic was to understand what is the best of this wireless technology and standards for our application. Today, as OEM, it's very interesting for me to have a deep understanding of this topology of, and I think that was the main topic, and it was successful. And now it's very interesting for me to discuss with the suppliers and all the BMS suppliers of this topic. We are now competent. We have competencies in this topic. So it's very interesting for us. And we had a lot of work on security topics that at the beginning we didn't want it to address because it appears to be very, very big topic for PhD. And in fact, we go also in these topics because you were very quick on your design and so on. So just to finish, of course, thank you very much to Nicola and Georgios because it was very pleasant to have this collaboration. It was very pleasure.
Thank you.
Thank you. That's all.
Thank you very much. Maybe Jonas?
Thank you so much for this presentation. Thank you so much for these last 3 excellent years. It was an honor for me to be part of this supervision team, advising team. You were really good as the candidate. I mean, honestly, it was a pleasure. You were always coming with a solution. You were like posing the questions, the problem, but you were always coming in the next meeting with things, solution, with ideas, and like going further and further and further. It was a challenge for us, for me and for Nicola as well, because we have been working with this subject for a long time, and it was really interesting application for us to manage to meet these constraints that wireless EMS comes with Renault. Thank you very much, Samuel, for this collaboration. It was a pleasure meeting you first and having such a smooth collaboration and very honest. It's really an ideal collaboration, and I'd like to thank you very much for this. It was a pleasure to visit you on your site, your facilities. Thank you for everything. I wish you all the best.
Thank you.
Have a bright future. Yeah, congratulations.
Thank you, Georgios.
So Nicola, you can.
Yes, thank you. I will not ask questions, but if I had to ask one question, it would be what did you not do? Because as soon as we ask something, you have a very good answer, even slight sometimes. So, and it's very representative of your work because it was very complete, I think, because somewhere thanks to the implementation, you noticed all the flows or all the problems, and then it brings us to deal with many different problems, and at the end, you succeed to make it something work in the car driving, which is very impressive. I wanted to remind as well, as you said, that it was during the pandemic crisis, because we start to forget about it a little bit, unfortunately. But at the time, it was the heart of the crisis, and it definitely slowed down our collaboration and your work. Because as you said, sometimes you had to only one day in the lab. I think you also took some hardware in your place sometimes to work on it. So it was very difficult, and honestly, we don't see this difficulty at the end. Now that we see the result.
I say.
He always has a picture to show. And yes, like Yorgo said, it was very nice that when we were talking about the problem, then you studied the state of the art, you came up with the solutions that you implemented, tested, and enhanced with the result of the implementation. And I also thank, of course, TI and Renaud, because I think it was a very good collaboration we had these last few years. It's the second PhD student who defended on this topic, and I think it was a very successful project that we conducted over these last 4 or 5 years, something like this. So thank you very much.
Thanks to you. It was a pleasure for me too.
Thank you very much. So I think we will stop this examination part and go for the jury deliberation. I don't know where.
Yes, we move to another room. If Carlo, Shaolin, and Michael, you know, I sent you another link on which you can connect, so we can deliberate together.
So thank you.
We can leave this session on WebEx, and
Okay.
so after when you come back, they can connect again.
Okay, perfect.
Si je peux.
Non, ça marche. J'ai des libérations au cours, et puis... C'est bon. C'est bon.
Mais on peut laisser les lights, non?
Ouais, je vais juste mettre qu'il y a la délibération, pour que les gens...
Ok.
Bravo, belle presse.
Merci. C'est bon, c'est Julien.
Oui, c'était vraiment...
Aïe, c'est pas grave. C'est carré.
Voilà.
Ouais.
Multi-message, délibération en cours.
Voilà. Tu as un pro des YouTube live.
Bah, je stream un peu sur Twitch, donc j'ai l'habitude de faire les trucs.
Mais vous faites ça toujours pour les tests ou c'est...
Ça dépend, en fait, ça dépend des gens. Si les gens me demandent ou pas de le faire, je sais qu'on on avait commencé à le faire pour l'HDR de cours qu'on avait fait.
Ouais.
Donc du coup, bah, il y a tendance à me demander, Nico, il en à chaque fois si je peux le faire. Moi, ça me dérange pas.
Ouais.
Et pas tout le monde le fait. Là, on avait une thèse hier, au final, je ne l'ai pas fait. Mais là, on va voir, peut-être qu'on va le...
Parce que c'est un super, ça fonctionne super bien.
Ouais. Moi, c'est pas très compliqué à mettre en place. Donc.
Ouais. Ah, c'est cool.
Bon, je dois faire quelques trucs que je reviens après.
Esa era la idea que quería que fuera muy claro. Pero el contexto explica que preguntas para la respuesta super fluida. Sí, que tenía sí. No, el cuadro ahorita, pero el sitio. Ah, sí. Ellos deberían para ¿vas a hacer trabajo en la operación? No, ahorita es distinto. Pero también quiero. Pues ya no llega. Es otra cosa, esto es de verdad 3 años ahí. Sí. Muy chévere. Oh, estoy cansado. Sí. Alicia debe sentir ahí que termina siendo un buen mix, compartiendo mix y pantalla hasta que llegues a tu familia. ¿Y tú tuvo el link? Sí, ya llegó a la mitad. ¿A la mitad? A la mitad, pues. O sea, miento. Digo, ¿cómo era eso? Para la sí, para. Siempre estaba viendo. Sí, yo me comparto porque después me digo para yo no sé. Porque tú le envías el link que envías el link. Sí, se le envía todo. Pero entonces, pero después te digo que yo no envié nada. En realidad, mi hermano fue el que encontró el link en el canal de mi tutor y él compartió a todo el mundo. Menos a eso. Pero no te preocupes que yo grabé mucho. Gracias.
Alors,
C'est bien passé.
c'est fini là ou c'est...
Non, délibération.
Sans délibération.
C'est en délibération, oui.
Ok. Bon bah, je reviendrai. C'est bien passé les questions?
Et oui, c'était super bien.
Ok, parfait. Félicitations.
Merci. Oui, est-ce que si il y a... Non, je sais pas. Pas mucho. Tengo mucha resistencia. Sí, sí. Buena. Buena. Qué mal. Oh, me cansé. Sí. También, muy chévere que los jurados entendieron que hubo mucho más detrás. Muy chévere. Sí. Sí. Ay, sí, estoy relajado. Sí, está liado.
Sí, sí. Y ya. Ya. No, sí, igual va a estar bien. Sí, ahí solo llegan allí.
Pues había estaban aquí otros doctorantes. No, además los que habían acá, hay unas ocho, pues eran cuatro jurados, dos invitados y luego mis tres tutores. De Texas era invitada, sí. Pero la de Texas, de Shaolin y Patrick Pasta, director de la región. Sí, sí. Ay, sí. Sí. ¿Cómo estuvieron largas las preguntas? O sea, se haciendo preguntas larguísimas. Sí. Pues era un montón de preguntas. Sí, ya. Sí, sí, ya. Y es que no aprendí el link también. Yo les envié el link mal y fue el link que encontró el link. Pero ya estaba con una presentación. Igual Pablo tenía videollamada entre cámara. Ahí está Pablo.
Contentos, orgullosos de su hijo. Estuvo muy bien, muy buena la presentación. Prefiero el inglés, hasta yo entendí que no es mi dominio técnico, pero sí, estuvo muy bueno. No, y los jurados súper tesos, ¿no? O sea, muy buenos, más o menos. Las preguntas difíciles también, pero las responde todas.
Sí. Ah, estuvieron buenas las preguntas. Estuvo interesante la.
Ah, yo tenía una pregunta.
¿Y por qué no hay poeta?
Ay, sí. Ay. Ay, sí. Estoy chévere porque. ¿Qué tal? Bien. ¿Ocupas algo? ¿Qué? ¿Ocupas algo de vez? Sí, sí. Igual no hay nadie, o sea, también. Bien. Sí, estuvo bien, ¿cierto? Sí. Siempre muy interesante. Sí, me has preguntado a mí una pregunta de Texas de la red neuronal, no sé qué. Estaba haciendo publicidad cuando carajo se lo pensaba en la red neuronal. Muy grande. Pues sí, porque yo era como, pues sí, me parece muy buena tu profecía, siempre más les decía, es muy conchado.
Sí, va a ser sincero. A ver, creo que me gusta. Sí. Funcionaba bien el vídeo y todo. Wow, ya que tiene un super sistema. Es un super sistema de Estados Unidos. Sí, a mí por eso también me gustaba el video. Ni siquiera yo entendía que se había escuchado bien. Pues sí, sí, se lo no, yo le iba a decir, de pronto queda muy grande de mi. Entonces, esta tiene un buen nick y buenas. ¿Y te dice Miguel? ¿Dónde se ubica la cámara de Javier? La cámara está allá atrás de la sala. Pero es que el micrófono es así, es que el micrófono es en todo lado. Hay como bolitas colgando de. Ah, mentiras, tienes razón, la cámara está allá. ¿Sabes qué pasa? Que hay dos cámaras. Hay una cámara para la videoconferencia, que era la de allá atrás que les mostré, que era la de. Y luego estaba esta cámara adelante para mis fans en YouTube. ¿Tenemos un qué? Pues, no sé. Fue, yo tenía hay varias primeras fue bastante. Sí. Sí, sí, pero por que no es, ellos decían después, yo te también inclusive, pero igual. Ya me pude preparar. A ver el partido de para. Bien, ahí está, ya. I was particular. Okay, ahí está ya. Bueno. Es la siguiente. Sí, es lo que me vi.
Bueno,
J'ai plus de batterie.
es como en el la tercera es súper importante y después esto el tiempo que suele tener proyecto y pasar esto ya no se puede y por ejemplo pero sí, nosotros pueden estar en ciertos eso fue un amigo que yo creo que no sé qué me parece que ahora los presentes que tenemos ya espero que te esperes.
Felix? Any?
Rien?
Je suppose que ça va arriver bientôt.
Ah ouais.
Ça sera reconnecté ici.
D'accord.
Je suis sûr.
Ah oui, d'emblée la retransmission sur les canaux qui sont
Ben, en fait, au lieu de dans la partie conseil,
Je suis pas du côté jury.
Au lieu de dire j'ai un slot et après je refais je réutilise le groupe par management. Je n'ai pas besoin de remettre mon groupe par management. Juste pour vous donner un peu plus de slots de temps en temps dans vos leçons, ceux que je sais qui sont pas là. Et donc, tu peux gagner plus de temps. Parce que tu n'as pas le groupe par management.
Ah ouais,
Ok.
We did not see how the handsome were. You have to explain. So, are we all there, or do we have to wait until people connect back?
I think we're good.
We are good?
Yes. Yes.
So Fabian, the jury is very happy to grade you, to grant you the title of doctor because of a lot of various reasons. So first, you delivered a very clear and pedagogical presentation of your PhD research work, where you designed and implemented a robust wireless battery management system for electrical vehicles. Wireless battery management is an emerging application of wireless networks, which is seen as having a huge potential impact on future electrical vehicles, and which is applicable to other domains, and you showed that in your presentation. And you successfully managed in your presentation to show the breadth of your contributions, going from reliable and energy-efficient wireless protocol design to practical experimental work on a real electrical vehicle. Your talk was well structured and had very clear illustrations. Really, the jury really liked that. You have been able, in your answer to the numerous questions, to show the depth of your understanding of your research topic and show how you carefully built upon the state of the art to provide original research. This is very important for your future development. And more important, you have been even at the end be able to highlight the open topical research questions and avenues for the future works. So for all these reasons, the jury unanimously grants you the title of Doctor of Informatics of the École Nationale Supérieure Mines Télécom Atlantique Bretagne Pays de Loire IMT Atlantique. Congratulations.
Very good. Congratulations.
Congratulations.
Yeah, thank you so much. I'm
Feeling different?
very happy. Yeah, I'm feeling different. I'm relaxed now.
You didn't seem to be stressed at all.
No.
Really? That's a really good point because I was kind of stressful. It was kind of stressful to prepare the presentation because I wanted to make it like very clear. I wanted to transmit the message as clear as it was possible, and I'm glad that it was possible and that you liked the presentation. So thank you so much.
Fantastic.
Bravo.
Congratulations.
Bravo.
Did you lose some buckets?
I don't know. No, 100% but we are used to close. But we made 15,000 retransmissions.
Congratulations, man.
Thank you so much.
Yeah. Fantastic.
Yeah, thank you.
Very cool to see you kind of grow in all this.
I'm so glad that you are here actually.
Sure.
I had
How could I miss it?
internship at India at the beginning, so it was very nice to have that you remember.
Very cool.
We have 4 right now. Maybe you want to say some thank you to the guys in this so that we close your panels.
Okay, no, I just want to thank you all for being here, for the jury members online. It's a real honor for me to have you as part of this jury. So just thank you so much. Hope that we will meet again in any other opportunity. So thank you.
Fabian, also on my side, very well done. It was really a pleasure for us actually to read your thesis and to see your beautiful work. So congrats. Enjoy the moment.
Thank you so much.
Bravo Fabian, c'était super. Bravo.
Ah, merci.
Et désolé encore une fois de ne pas avoir pu me déplacer, j'aurais préféré être sur place, mais voilà, même à distance, c'était top.
Merci beaucoup Patrick.
À très bientôt. Au revoir.
À très bientôt, au revoir.
Au revoir, merci.
You do have some congratulations in the chat.
Here I will finish too.
You can also try to mute Mikael. I think he also trying to congratulate.
We are trying to leave it.
Yeah, I just want to congratulate for a very good piece of work. Celebrate tonight.
Thank you. I will. Thank you so much.
Has to be one of my.
Okay. Bye.
All the best.
Thank you, bye-bye.
Ok.
Thank you so much, Carl.
Thank
Thank you so much.
Il y a toujours les...
Thank you very much.
Bueno.
Au revoir.
Bye-bye.
Je vais parler en español.
Vas-y, fais-toi plaisir.
Pues ya acabamos. Going to speak with my family. Ya acabamos. No sé, lo logré. Muchas gracias a todos por haberse conectado. Espero que hayan entendido un poco. O tal vez no, pero pues es muy importante para mí que hayan estado aquí conmigo y pues ya lo logramos. Muchas gracias. C'est bon, tu peux couper. Adiós.